illustrate the point. So I want to set up a simple problem that has two boxes. And the boxes are just resting on the ground. So I'll start with, let's see, the ground. And let's make this one that has few complications. So we'll say that for right now, this surface is nice and slippery. There's no friction to worry about. And I have a larger box. And a smaller box. So one of them 10 kilograms, one of them 6 kilograms. Something external to the system, like say a person, presses on the first box with a force of 25 newtons. I want to figure out what happens to this system. Now, I'm going to start using some words here, and when I use them, I want to kind of put them off to the side a little bit. You're going to start hearing me use the word system more and more now. The two boxes constitute a system. They are connected together because they are touching. What happens to one is shared by the other. Would you agree that the blue box can't move to the right without the green box moving to the right as well? So they constitute a system. There are individual objects within a system, but we can talk about forces that are external to a system and forces that are internal to a system. So you'll hear me use the word external and internal. Please pay attention to those words. They have meaning, and I'll help define them, but these are some words that are sometimes difficult to define. System is sometimes hard to define. Now, what I would like you to do is apply our force concept model. We have done this many times already. The only major difference is that you have to apply it to two objects at once. But remember, the model requires that each object be treated individually. So I'm taking and putting two dots down. I'm going to pick one of these boxes to evaluate, and then I'm going to pick the other box to evaluate. So let's start with the blue box. Name a force acting on the blue box. Gravity. So that's an arrow that is 100 units downwards, right? 10 times 10. So I'm going to draw an arrow downwards that represents 100. So that's my 100. And it's best that you start realizing this next test, the proportional size to the arrows is going to be important. So name another one. All right, so when you start saying words like normal force now, you're probably going to have to narrow it down. So I heard the word normal force, but normal force from what? Because I see two surfaces that are connected together, right? Or at least two surfaces that are touching. The box is touching the ground. That's got to be a normal force. How would I draw the arrow for that normal force? The ground pushes upwards on the box. I need to draw it large enough so that it's equal in size to the weight that I already drew. Now I'm going to get this one out of the way, but there's got to be a 25 Newton force too, right? That's the external force. Somebody's pushing on the boxes. Some of you are going to put that on both boxes. Don't. The 25 Newton force doesn't act on the green box. It acts on the blue box. However, is there any other force acting on the blue box? Has to be. What's it in contact with? It's in contact with another box. That's another surface. So there must be a normal force on the blue box. And it's not arbitrary the direction. It has to be perpendicular to the surface. So what direction should I draw that force? To the left or to the right? Just point in the direction I should draw that force. I'm not taking this lightly. I drew my arrow smaller than the 25. I think the system is going to accelerate to the right. So I purposely made the forces look unbalanced. You should do that. You should be careful to think about that. If the system's going to accelerate, it's going to accelerate this way. I am making this the positive acceleration or the positive direction. I'm making choices about how I draw the arrows now. And none of these choices are arbitrary. When you guys are taking notes, take notes that tell you how we did this. So I guarantee your homework's got like 20 of these. And just setting them up takes some time. Now we gotta do the other dot too, right? You do that one real fast. Show me what you should draw for that one. I'll take a walk around and look. You now need to be cognizant of the size of the forces when you draw your arrows. It makes a big difference, and their grade is based on their relative size. Get the direction wrong, everything's wrong. But now the direction has to be right, and the relative size is part of the grading. So when you drew the downward arrow, did you draw it smaller than 100? It should be, because this box has a weight of 60 newtons. And the upward arrow should be the same size as the downward arrow, because those should show balance. But also, this is our Newton's third law pair. I should be drawing an arrow over here that is the same size as the arrow over here. Now, I named these two things something different. I said NG, from normal force from the green box, and NB, normal force from the blue box. But if they are a Newton's third law pair, they are the same size. That's important. It's a detail you need to know. By Newton's third law, those two forces have to be equal but opposite. So their size has to be the same. So the symbol we use is the same. Now there's a lot of N's everywhere. Be aware, you're probably going to need to differentiate. Maybe I'll put G on the one from the ground, so I know that those are from the ground. But I know this one and this one have to be the same size. Now you know how to do more things than this. I don't care about the Y direction, but it looks like something's happening in the X direction. Part of the problem you guys are having with your test is you can't write things down out of context. Like you can't just have a floating mg sine theta and think that means something. Start someplace. These problems are always going to start with either net force equals 0 or net force equals ma. Pick one and stick with it. Because even if you can't get full credit, you can pick one of those and apply the rules to it. So if you chose wrong for ma or 0, at least you'll get more points later because you show you can apply the rule. The rule says to add up all the forces that are in the x direction. Take into account direction. I made to the right positive, so 25 minus n equals ma. I'm just applying the rule. They point in opposite directions, so there should be a minus sign in there. Apply the rule. The rule isn't complicated. Your knowledge of it seems to be, but the rule isn't complicated. Now I have to apply it to both boxes. I'm pretty sure both boxes are going to move, so this box, now I have m for both, so I can say that this is 25 minus normal equals 10a, and this one is normal equals 6a. Of course, I have a page now with just stuff written everywhere. So let's make sure we know what's important here. We did all of that work to get to here. Newton's laws generate relationships. We have generated relationships, but we generated them for two different objects. We should ask ourselves, is the acceleration the same for both boxes? That's not an unreasonable question, but think about it just logically. If the blue box accelerates faster than the green box, that means the blue box is going through the green box, right? Does that seem like what's going to happen? And if the green box is accelerating faster than the blue box, then they're separating. Do you think that's what's going to happen? I think that's unlikely. What would make the green box go faster? What would separate them? I think the only reason the green box is going to move at all is because it's touching the blue box. I'm just trying to work logic here. I'm not trying to create fantasy. So I don't think it's unreasonable to say, I believe both boxes will have the same acceleration. But you should evaluate that. This is something new. When you have multiple objects connected together, you should evaluate their motion. This is a new rule. Didn't exist before because never had more than one object. If you want the best way to do this, the easiest way, make the direction of acceleration positive for all of your objects. If you want this to work out easy for you, and you should put that in a box and highlight it. If you want this to work out for you and you have more than one object, when you have more than one object, make the direction of the acceleration positive for all of the objects. This one's easy. They're both going in the same direction. They won't always be. If you look at what I have set up here, I have something that's going to go down while something else is going to go to the right. Making positive the direction of the acceleration might change if you have things like pulleys in there. So make the positive direction the direction of the acceleration for all of your objects. It'll make things easier. Now we're actually pretty close to being done analyzing this. You may not see it, but these two things are related. Do you see it in there? Newton's third law shows up. I have normal and minus normal, two forces that are equal and opposite. And if you've done all this correctly, they will show up as being equal and opposite. In fact, I can just add these two things together. I just line up the equal signs. I add down on the right side, I'll get 10a plus 6a. And on the other side, I'll get 25 minus n plus n. I just added the two equations together. Now, normally I wouldn't write the minus n and plus n. I would just cancel them out. I'm writing it in this class because this class needs an extra step. Okay? Just like I probably wouldn't write 10 plus 6. I'd probably just write 16. But this class needs an extra step, so you got your extra step now. So I get 25 equals 16a. Like I said from the beginning, Newton's laws can tell you the size of a force or they can tell you an acceleration. They have told us an acceleration. This is how fast the system accelerates. We can find out more stuff. Like we could find out what n is. Can you find out what n is? Please do. Take a minute. You can find it in either one of those, but it's probably easier to use one than the other. So somebody did 6 times 1.56. I should call on all the people who didn't bother to reach for a calculator, have them look at me like I'm an idiot, and say, oh, you called on me just because I'm sitting back there with my pencil in my hand. 9 point what? 4. Now, not particularly tough. In fact, I'd argue that most of you probably felt that this was okay, something that you could do. So I want you to kind of prove that that's true because I want to show you something. I'm not even going to change this very much. I want you to repeat the exact same thing. I mean, don't change hardly anything except I want the order of the boxes to be different. Because I want you to think about what would that change if it was the green box first and then the blue box. Try it really quick. Do all the same things we just did. 10 kilograms, 6 kilograms, and a 25 Newton force, but the force is pushing on the green box this time. Hustle, because we only have a few minutes, because today is a special schedule. That's what I really want. I want that normal force. Hurry, bell rings in 2 minutes. We gotta hurry. Something like this. I didn't draw the up and down ones. I don't need them. Did I need the up and down ones last time? As long as there's no friction, I'm not really going to need those normal forces. Need these, though. And did you get 25 minus n equals 6a? Seems good, right? And then maybe n equals 10a? Is that what you guys got? You put these together, do you see you're going to get the exact same thing? I want to show you that. So we put them together, add them up, and one of the things you'll get is the systems equation. You'll notice that this is the mass of the system, right? All the masses together, added together. And this is the external force on the system, but you should see that the acceleration was the same. I know you guys have to pack up, so I'll do this last part. Normal equals 10 times 1.56. That means that in this case, the normal force was 50% bigger when I push from the other side. That's what we need to explore tomorrow.